Hello, everyone. Welcome back to the local time evening session. And the first talk of our session today is by Zhou, and he's going to talk about the quantum approximate optimization algorithm and the Sherrington-Kirkpatrick model at infinite size. That's a mouthful. Take it away, Leo.
Thank you, Jonas, for the nice introduction. Hi, everyone. I'm Leo. I'm excited to share some recent results on quantum optimization with you guys today. And this is a joint work done with Eddie Farhi, Jeffrey Goldstone, and Sam Gutmann. So the problem we're interested in solving are combinatorial optimization problems. And these are problems that are basically given a cost function defined on n bit strings. We want to find a bit string assignment so that the cost function is maximized. And typically a cost function is written as a sum over different clauses, and each clause could be, for example, correspond to some constraints on a edge on a graph, for example. And one very prototypical example of a combinatorial optimization problem and it's happened to be NP complete, and that's the problem of max cut. And this is a problem where you're given a graph, you find a bipartition of vertices so that the number of edges between them is maximized. And you can write the cost function as a sum over the different edges, where each edge has a term that looks like this, which evaluates to 1 if the bits on the edge disagree and 0 if they agree. So you can indeed see that we're really trying to maximize the number of disagreements. And another problem, which will be the main focus of the talk today, is the Sherrington-Kirkpatrick model. And this is the problem where the cost function is understood as the energy maximization of n spins, which are all-to-all connected. And the interaction between spins are these Jij variables, which can be, say, drawn from the standard normal distribution, or you can also choose them uniformly from plus or minus 1. In fact, any reasonable distribution with mean 0 and variance 1 describe the same model. And this problem is actually kind of connected to max cut because it turns out that max cut on Erdos-Renyi graphs is equivalent to the SK model in the average case. And for those of you who don't know, Erdos-Renyi graphs are those where every edge on the graph is chosen to exist independently with uniform probability. Now we want to solve this combinatorial optimization problem with a quantum algorithm, and a very leading candidate for these problems is the quantum approximate optimization algorithm, or QAOA. And this was proposed in 2014. And the idea is that you want to assign a qubit to each of the vertex on the graph, and you want to prepare them starting in the plus state. And you want to evolve them with two unitaries. The first one is just the evolution under the cost function in the z basis. And the other one is this B Hamiltonian, which is sum of sigma x's. So this just corresponds to a single qubit rotation in the x direction. And say you want to repeat this for p layers, and you measure in the end in the z basis, and you will get a bit string. Hopefully, with the nice with a good parameter gamma and beta, you can maximize the cost function that this bit string will give you. But in the original proposal, the idea is to sort of run this experiment many times, and you take the expectation value, the average, and then you feed that to a classical computer in a closed feedback loop to optimize the parameters gamma and beta so that you can get as good of a cost function value as possible. Now, this algorithm is attractive for many reasons. One is sort of very simple. It only requires 2 different unitaries. And also, you can see that just manifestly, this algorithm can only improve as the depth of the number of layers, p, increases. And also, there's a very nice mathematical fact that as p goes to infinity, this algorithm can always get the global optimum for any instance. Well, that is nice, but often this sort of relies on the sort of this reduction to the fact that you can approximate the quantum adiabatic algorithm with the QAOA in the infinite depth limit that correspond to an infinite time. So it's nice, but it's not very useful because in principle p needs to grow exponentially with n, and often we're interested in the regime where p is some polynomial or even logarithmic in n. Now. So this work that I will present today would be focusing on sort of evaluating the performance of this algorithm for the Sherrington-Kirkpatrick model. But before I go to my main results, I would have to review a little bit of what has been done before. So in the past, the analysis of the QAOA's performance have been mostly done via this subgraph method. So as an example, I'll again talk about max cut now on 3 regular graphs. So these are graphs where each vertex is connected to exactly 3 neighbors. And this is the cost function again. So if you want to evaluate, say, the expectation value of the cost function at p equals 1, it will basically consist of terms that look like this. So for each edge, you have a zj, zk term, and then that's going to be conjugated by the 2 different unitaries. And if you sort of look at this operator, you can see that any of the qubits that don't sort of directly connect to j and k will sort of commute through. So that will mean that this operator inside the bracket is only supported on 3 different types of subgraphs when the original graph is 3 regular. For example, if you consider starting on an edge between 3 and 4, you will correspond to a subgraph of type 2. If you start with an edge that's connected between 8 and 14, you'll get a subgraph that looks like this. So you can see that just by sort of going through the graph, no matter how large it is, and just looking at every edge and see what kind of subgraph it corresponds to, you can essentially evaluate what the cost function is for arbitrary size graph, because each of the terms will only depend on a graph of a subgraph of size 4, 5, or 6, which can be simulated on just a classical computer using, say, exact diagonalization. And this is this was used in the original QAOA paper to show that for 3 regular max cut, you can get a worst case guarantee of being able to achieve a cut that's sort of 69% times the maximum at the lowest depth, p equals 1. So this idea was nice and non-trivial because it really provided the first sort of performance analysis and guarantee for quantum optimization. But it's very difficult to generalize this for higher p because the complexity of the classical calculations grows doubly exponentially in p. To see this, you can see it's because the size of the subgraph grows exponentially in the degree and depth. And because if you want to actually simulate this expectation value, if you want to evaluate that, you would need to use a Hilbert space size that's growing exponentially in the size of the subgraph. So together, using the subgraph method, the complexity is 2 to the p, and you can see that very quickly, even for p equals 2 and 3, this is essentially intractable. Now, another result that came out of this subgraph analysis is this phenomenon called landscape independence. So this is the idea that if you look at the expectation value of the cost function for a given graph, of course, it depends on the graph, right? Because the cost function itself depends on the graph structure. And the wave function, since it depends on the unitary that depends on the cost function, will also depends on the graph structure itself. But it turns out that if you take the n goes to infinity limit, because of the fact that this expectation value, which just depends on sort of the subgraph counting, and in a random graph, the fraction of different subgraph type will sort of concentrate by just law of large numbers. You can see that this expectation value will concentrate at a value that's sort of independent of the graph up to some sort of finite size effect. And more pictorially, what this means is that if you look at 2 different graphs and you look at the expectation value of the cost function, they will look essentially the same in the QAOA parameter space. Well, this is very nice because it will really save us a lot in terms of finding the optimal parameters, because if you take a random instance from a given ensemble, like through regular graph, you can simply work hard to find the optimal parameters for one instance, and then you can use that for essentially all the other instances in the same ensemble. But because of this sort of subgraph method, there's also a negative result that came out, because you can also use the same argument to show that low depth QAOA, because of the fact that it only sees like a subgraph, not the whole graph, it necessarily has limited performance. And to see this, for example, you can consider the limitation in the worst case, in the sense that if you consider the irregular graphs, when the number of layers of QAOA is much less than log n, the subgraph that you see are going to be mostly trees. That basically means that you cannot really distinguish the bipartite regular graphs in the ensemble versus a typical one, which is highly frustrated. So because of the fact that you can never do better than the maximum, the QAOA would just get a value that's roughly the typical value, and that's much lower than the bipartite case. Now I will move on to our result, and before that, I will just need to tell you a bit more about the Sherrington-Kirkpatrick model. So again, this is a cost function essentially defined on a complete graph with random sign couplings. And because of the fact that the complete graph obviously has unbounded vertex degree, we don't have this issue of the low depth limitation because the QAOA sees the whole graph at p equals 2. Now, for the worst case, estimating the maximum energy of this cost function to even a factor that's like polylog n, it turns out to be NP hard. But if you want to just look at the typical case, there's actually a very famous result by Giorgio Parisi in the late 70s that predicted that the maximum energy for almost every instance drawn from this ensemble is essentially this number 0.763, which we will call the Parisi constant. And this is actually a very non-trivial result. It used all these very exotic techniques, introduced all these concepts like replica symmetry breaking, and started the whole field of spin glass theory. And it was so complicated that people didn't really were able to rigorously prove that it was correct until decades later. And the final piece of the puzzle was put together by a French mathematician in Telegram. Well, that's very nice since we know the maximum energy, but the Parisi result doesn't actually tell us how to construct the solution. It doesn't tell us what the bit string is. So what's the complexity of solving the SK model in the typical case? Well, you can try simulating, but it's believed to fail for this problem because of the spin glass nature of the solution space. And what that means is that we believe that if you run simulating annealing for any sub-exponential time, you will get stuck at an energy just sort of below the maximum energy that's given by the Parisi value. You can also try, say, a convex relaxation method like a semi-definite programming, and that will give you a cost function that's c over n that's equal to 2 over pi, which is roughly 0.636. So that's kind of closer to the Parisi value, and it's provable. But it's not quite there yet. And very recently, assuming a conjecture that the SK model does not have a property called the overlap gap property, Andrea Montanari gave an algorithm that is able to basically output any kind of epsilon approximate solution z in time that's only polynomial in the system size and the epsilon. So, assuming this conjecture is true, then there's really not that much room for improvement upon this classical algorithm that was discovered by Montanari. But we would still like to see if the QAOA can at least match the performance. So now I'll move on to our main result. And the first one is that we're actually able to evaluate the QAOA's performance applied to the SK model at very high depth P. In the sense that we're able to give a formula for the expected cost function average over the different instances and the procedure to evaluate this formula has a complexity that's roughly 16 to the p. This is much better than the doubly exponential time that's required by the subgraph method. So we've made progress. And even though the complexity is exponential, we're still able to sort of take this to p equals 12. And as you can plotting the maximum energy achieved normalized by n as a function of 1 over p. And as p increases, you sort of see a steady increase in the energy. And interestingly, at p equals 11 is able to surpass the value achieved by semi-definite programming. So at least we're able to be semi-definite programming, but it's not clear, exactly how fast or where the QAOA will converge to what value would the QAOA converge to, or how fast it will. Now, a second result that we were able to show is there's also a concentration of the QAOA on the SK model, even though the degree of the graph bounded. And what this means is that if you look at sort of the the expectation value of function square, and that's equal to the square of the expectation value. And this implies actually, and the first fact is concentration over instances. And this is what I referred to earlier as landscape independence. And what that means is that if you look at two different instances of the SK model, the QAOA objective function landscape will look essentially the same. But there's also another concentration result, which is concentration over measurements. And this is saying that if you look at the output distribution of a QAOA circuit of any given relay, and you will see that the cost function value that you get will also concentrate at the quantum expectation value. So there's very, very small variance in the energy outputted by the QAOA. So together, what this means is that, as n goes to infinity, and the probability basically goes to 1, that if you apply the way and measure in the z basis, you will give you a bit string that has a cost function value that's equal to roughly the quantum expectation value, which is itself this graph instance independent value that we call VP. I will now sort of sketch a little bit of the basic key idea behind our result. And this is essentially the main reason why we make such progress is we are able to really average over the different instances. So I would like to first go back to Parisi's formalisms. So in order to actually find the maximum energy, Parisi actually used some very, very delicate tricks. And what he did is he tried to evaluate the energy. So the free energy is the log of the partition function. So as you can see that when the temperature T goes to 0, this is dominated by the maximum energy state. So this is how you get the maximum. And you're maybe tempted to sort of switch the log and the expectation over the different instances, because if you can do that, then this averaging is very easy because, if you, for example, take the J's to be Gaussian, this is just going to be a Gaussian integral. But even though this is sort of, what you might want to be tempted to do, this is actually incorrect because you cannot just switch log and expectation. And the whole business of Parisi is really trying to figure out how to take this average with the log inside. And what he did is basically, use this replica trick of, having k different copies, k different replicas of a given instance, and then taking the average, and then taking the log. But then you take the number of copies to go to 0. For some reason. So you can see it's a little bit, bizarre. And this is one of the reasons why, in order to show that this was actually mathematically correct, it took 20-something years. But for QAOA, averaging over the different instances is much easier because, for example, let's consider P equals 1 again. And we want to evaluate the cost function expectation average over the instances normalized by n. And if you just sort of expand out the circuit, what you have is a cost function that's conjugated by the two different unitaries that's in the QAOA circuit. And then what we did is that we can insert complete sets of states. So these z variables are the different n-bit strings that you would sum over. And you notice that the j's that we'll be averaging over appears only in c's. And these C's sort of just appear, either downstairs here in the cost function or upstairs in the phase. And we can use the fact that, for a random variable J and for some small number phi, the expectation of e to the ij phi is just 1 minus roughly 1 minus 1/2 phi square. And, the expectation of J times e to the ij phi would just be roughly I phi. And it's justified because this phi, what appears in the exponential here, it has this 1 over square root of n factor. So indeed, we can take this, to be small in the n goes to the limit. So applying this kind of identity, you can then rewrite the cost function average of the j's as sort of this sum bit strings with sort of products that doesn't depend on the j's anymore. And because of the fact that this expression doesn't depend on the j, there's an intrinsic permutation symmetry in the sense that if you just swap the locations of the n different bits, it does not really change the outcome inside the sum. But what we did was that we can reach this permutation symmetry to what we call the configuration basis. So what I mean is that if you take, for example, two different bit strings that you're going to sum over, Z1 and Z2, and say this is what they look like. And you can just look at the locations where the two bit strings are either both plus and plus or minus, minus and plus, and minus. And these are the only possible configuration that the two bit strings can take. And the number of times where each of these configurations appear, they have to sum up to n. And basically that what this allows you to do is that instead of summing over the bit strings, you can sum over configurations, which only requires you to sum over, in this case, 4 different things. There's only 4 different n's. And for general P, you can sort of see that there will be sort of a 2P bit strings that's going to be inserted. And that basically means that there will be 2 to the 2P configurations. And this is what gives us the exponential in P complexity in our calculation. Now, if you just turn the crank, you will basically arrive at the answer. For example, at P equals 1, we get an answer that's just gamma times e to the minus 2 gamma squared times sine 4 beta. And this is simple enough to optimize. For example, if you just stare at it, you can see that the optimum occurs at beta equals pi over 8 and gamma equals 1/2. And this gives you a maximum value of 0.303. You can also apply the same technique to evaluate different moments, and this is what gives us concentration. And another point that I would like to make here is that if you consider the generic performance of QAOA, so just some random parameters that you would choose versus the optimized parameters, what do you expect? Well, it seems to suggest from this formula that the cost function for any random parameter would scale with n. That's actually not true, because if you, for instance, consider if you choose the couplings to be plus or minus 1, then if you kind of remember how the cost function is defined, you can see that gamma, the parameter gamma, is periodic between 0 and square root of n times pi. And beta is periodic between 0 and pi over 2. So what that means is that, so the right parameter space to look at is sort of, is basically when gamma has to span over a range that grows with n. So for a random point chosen in this parameter range, you will get a generic performance of QAOA that scales exponentially small in n. So it's a very good thing that we're able to calculate the parameters, optimize the parameters in advance, and find the true optimum parameters, which are much better than a typical generic case. And for higher P, as I mentioned, our current method uses exponential memory and time. But we're able to take it up to P equals 12, as I mentioned. So we started at 0.303 at P equals 1, and at P equals 11, we get 0.639, which is better than the 2 over pi number that's achieved by the semi-definite programming. And I'm just showing again the plot of the performance. So we do see that the performance does steadily increase as P increases. But it's not really obvious where it will converge, and you might actually wonder why, because as I mentioned in one of the first slides, that as P goes to infinity, we should expect the QAOA to find the global optimum, right? But there's a very subtle issue involving order of limits. It's because here we're taking the order of limit of n goes to infinity first, and then P goes to infinity. But the argument presented in one of the first slides is only valid if you fix n and take P goes to infinity. So we don't really know whether we can actually switch this limit, while maintaining the mathematical correctness. But assuming somehow you can, and then you will be able to show that the value achieved in the infinite size limit of the QAOA does converge to the Parisi value. Then you can say, for example, try to fit a power law function. And if we try to do that, we'll estimate that roughly speaking, the approximation ratio that you get is sort of roughly approaches 1 roughly as a function of 1 over P to say 0.9 power. I will sum up my talk by just reminding you that we have analytically obtained a formula for the typical case performance of the QAOA applied to the SK model at very high P. Even though the current evaluation of our formula takes 16 to the P complexity, but it may be improvable in the future. And our result also shows that QAOA is able to surpass semidefinite programming at p equals 11. And we're also able to show concentration over both the instances and measurements. Now, for future work, we want to actually be able to do this limit switching and show that QAOA converges to the pre-C value as p equals to infinity. But more broadly, we're interested in applying our technique of averaging over instances to harder problems for potentially approvables. We can look at the Q-spin model, which is basically the SK model, but instead of just two-body coupling, you have a Q-body coupling. And it turns out that this problem is actually provably hard for classical algorithms, including Montanari's algorithm, because of the existence of the overlap gap property. In particular, it was found recently that Montanari's algorithm is stuck around 98.4% approximation ratio for the three-spin model. And we're currently working on this, and I would just like to share that at p equals 1, we're able to get 33%, and we're working hard to improve our techniques to higher p, and we believe that this is a very fruitful way to potentially show a provable speed up of for quantum optimization. That's it.
All right. Okay, Leo, thank you for the talk. We have time for one quick question, I think. So I have a question here from Ruslan Shaidulin. He says, he asks, the concentration result do not come from locality and the corresponding, do the concentration results come from locality and the corresponding average over some small number of local subgraphs, or does the concentration have some other cause? So basically, what is the cause of the concentration in this, in your proof?
Yeah, that's a very good question. So in the early work on concentration, indeed, in order to show that it's correct rigorously, we rely on sort of the subgraph locality kind of intuition. But even in those early papers, it was sort of hinted that the same concentration result applies in the regime where the QAOA is non-local, where you see the whole graph. And in particular here, this is also one of the reasons why our concentration result is kind of novel, because the SK model, you see the whole graph even at p equals 2. So there is really any sense of locality. And so we believe that this concentration result, which is proven here in this case, is much broader and does not rely on just locality arguments.
All right, perfect. So there will also be a breakout room that I invite everyone to go to. There was a few more questions in the chat, actually. So Leo, I think the people in the chat will also go to the breakout room, and then you can answer the questions there. So thanks again for coming, and yeah, good luck in the breakout room.
Great, thank you.